Hey everybody, this is Larry. This is day 31st, the last day of August. Hit the like button, did I hit the right button? I think so, yeah, okay. I wasn't sure. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. Before we start, I guess we did this one recently or something. Before we start, what was I going to say? Oh yeah, today I ran a Yeezy 8 miles, which is just like a very slow pace, 8 miles. I think I bring it up because I think as we are trying very hard to get good at whatever we're working on, whether it's Leetcode or for me, been running and training for the marathon, it's okay to not have to go hard all the time, work on easy things, work on prompts. Remember, a lot of what you want to do, the only way you get better is by learning and also recovering from the learning, right? Meaning, getting good sleep, getting good rest, getting good food and nutritious and all these things, right? You don't have to go hard every day. It's okay to kind of work on easier problems from day to day and then kind of, ramp it up. And progress is not always going to be made in a week or a month, but, when you have all the hours add up over a year or maybe longer. I mean, I know some people have timelines and you have to kind of pace yourself and figure out, figure out how to get to where you want to be in certain timeline. Like for me, I have 2 months to kind of train, less than 2 months now, I think, maybe, give or take, for the marathon, right? So it is what it is, right? So that's the testing day, if you want to call it that. So I have to work hard and it's tiring, but I have to focus not on just the training, but on the recovery and on the rest and getting enough sleep and eating well, right? So it's the same thing with Leetcode, same idea, right? If you're not getting enough sleep, it doesn't matter how many problems you're solving, and it doesn't matter. And if you're not learning, it really doesn't matter how many problems you're solving, right? Same with my workout is that you have to focus on what you want. I say this a lot in previous times, and maybe in a different way. So today, maybe I'll say it a little bit differently, right? You have to focus on, try to figure out what it is that you're trying to win on, right? For me, I'm not trying to win every workout, right? Like every workout, I don't have to run a personal best and to look good or whatever, because that's not what training is for, right? I don't have to win every training. My thing is that I want to hit a goal at the race day, at the marathon, and that's it, right? Similarly, if you have like an interview where like it's okay to move a little bit deliberately, move a little bit slowly during studying and learning, and just focused on doing well on the interviews, not even the contest. That's why I always say that ratings are a little bit overrated, because it doesn't matter how you do, it's just about how much you're learning and how much you're recovering from the learning, right? Anyway, all right, that said, let's kind of take a look at today's problem and kind of focus on 1514, path with maximum probability. Didn't we do this literally, was it 2 days ago, 3 days ago, something like this? Did I make that up? Or was that a weekly problem? Did I make this up? No, we did this, right? I said it was Dijkstra. It is greedy because it is in one. Huh? Am I doing two sum? That's not right? We didn't do two sum. We definitely didn't do two sum today, or this week anyway. So wait, what was that? What day is that? Tuesday? I guess we could just check here. 26. So that's 4 days. What is going on here? Well, alright, I mean, I'm not going to do it again because, that's just kind of silly. So I'm just going to paste this. Let's see if it works. Yeah, I mean, I don't know what to say. Okay, well, I got a badge though. Yeah, I'm not going to do it again just because literally it's 3 days ago. You could check out that video. In fact, I'm going to paste that video up next. But yeah, that's all I have for today. I mean, I'm going to do an extra problem. But so you'll see me doing a bonus question, random problem. But for this problem, I don't know that I have anything new to add just because it's been 3 days. I didn't grow that much in 3 days. Definitely not in Dijkstra seeing anything. So yeah, that's all I have for today. Thanks for watching. Hope the intro is good. Maybe I need to, because I don't know if people's gonna watch this video because of my video from a few days ago. So I don't know. But hopefully the intro is good, and let me know in the comments if you watched the intro, just so that I don't know, maybe I'll repeat it tomorrow anyway. So if you watch this, then you know. But let me know in the comments how you feel about it, if it makes sense. And yeah, that's all I have for today. And you could watch the rest of me solving this problem now. Hey everybody, this is Larry. This is day 27 of the Leetcode Day Challenge. So hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's daily problem. I finally took a rest day. I have not skipped the gym in about 3 months, but I think it's time that I took a break. So today I feel a little bit better, but my body is still very sore, so we'll see how that goes in a couple of days. So today we have 1514, path with maximum probability. So you're given an undirected weighted graph of n nodes. Oh wait, one thing that I wanted to say before the problem is that I think we get tied up on these streaks, and I did as well, because I had a 50-day running streak and like a 70-day or maybe more just workout streak, because even on my running days off I go to the gym. But you know, at the end of the day, your goal is, you should figure out what your goals are, and my goal is not to have good workouts. My goal is to get good at things, right? Like running. My goal is not to perform well during the workouts. My goal is to perform well during the races, right? So I'm just trying to you know, rest and hopefully get to that. My back is a little sore, and I don't even know why. But I mean, I guess I ran like 12 miles yesterday, but still, or whatever, 13 miles, whatever it is. I don't know. Body's getting old. But anyway. So you're given an undirected graph of n nodes. You have edges, edge list, and an unweighted but probability. Why don't they just not put it as part of the edges? That's weird. Okay, but anyway, and they call it suck probability. I guess it means success, but still, what a terrible, what a terrible variable name. Anyway, parameter name. Okay, given start to end, find the path with the maximum probability of success. Okay. I mean, I think one thing to kind of realize in general, right, with the shortest path problems, or like just identify from shortest path algorithms anyway, is that they operate on the principle of greedy, right? They're all greedy because the idea, well, not all of them, but many of them are, right? Like Dijkstra's, BFS. I know that Bellman 4 technically is not greedy. Or maybe it is, I don't know. Depending on how you want to define it. But anyway, and the reason why greed works is that you can kind of say it in English, which is that the best path from A to B is, you know, you're trying to get from A to C, and you know, A goes to B and B goes to C or something like that, and the shortest path kind of connects them in that way, right? I didn't say it that well that time, I don't think, but that's basically the idea. So probability, I assume that we just kind of multiply the things instead, right? And if you think about multiplication, if you try to maximize the thing, then that, you know, if you just kind of take the greedy principle, it should be okay, right? You just want to get to a node with the maximum probability, because, and the path doesn't matter as long as you have the maximum probability in this particular problem, right? I mean, sometimes some problems will make it the path matter, and for example, like what you would call it, Hamiltonian path, right? The path matters because you cannot visit the same node twice, or something like this, or same path, yeah, same node, right? And the other one is the same edge, or the in cycle, right, or whatever. And so, yeah, so because I mean, maybe you can definitely try to prove it with greed, or prove the greedy algorithm, but in general, it is, you know, that's just the idea, right? Is that sorry, I don't know why I'm like, feel like I need to take some antihistamine or something. I'm just like maybe allergic to something in the apartment or something. I don't know. I just have trouble like speaking, as you can see. Like I'm swallowing a bit. So definitely my apologies if I'm talking a little bit slowly and deliberately. But in any case, I don't know. Maybe it's allergies. But yeah. So we can definitely do that, and we will just do that, and we'll have a shortest path idea of the shortest path. And like I said, right. If you're trying to go to path B of maximum probability, then it doesn't matter what the path is per se, right? So yeah, and here we're going to use Dijkstra's algorithm because it allows us to relax with the maximum probability because because the rate is the probability and the operation is just multiply, right? Because as you kind of multiply more and more, it just gets lower and lower. And of course, if given this idea, you have to make sure that there are no cycles, right? Or not that there are no cycles. Of course, there are cycles, but negative rate cycles, right? Or in this case, cycles that gives you more than one probability. Which is obviously just not possible. In fact, it shouldn't be possible that the suck probability is better than 100%. But you know, these are just kind of things that you assume. But sometimes some contest farms will you know, do really silly things about it. So yeah, okay. So let's get to it. Let's just say we can have times n, and that's basically our best thing, right? The other thing we want to do first though is convert the edges. Right? And then we put in an adjacency list. Right? I mean, today, again, maybe I'm not going to, I don't know, I'm just struggling today with talking. Like, I think I'm hearing a little bit better. I don't know, maybe there's some, like, allergy stuff, or, like, something I'm allergic to in the apartment. I don't know what it is, but I am definitely getting allergy symptoms. Maybe it's maybe there's a tree I'm allergic to. I don't know, I just came back from outside, so. Anyway, my apologies. But yeah, this is just converting to an adjacency list, where we have two things, right? Where one is the second node that we're connecting to, and the probability of going to it. And I assume that these are the probability is symmetric, meaning A goes to B and B goes to A are the same. It seems to seem that way, but you know, sometimes you have to read carefully because I don't know. I made a lot of mistakes being wrong before. So first we relax by saying best of start node is equal to 1.0 for 100%, and then we just put this in the heap, right? 1.0 start node, right? I don't know why I put it in a way in this case. And this is going to be just very standard whatchamacallit, Dijkstra's algorithm. I'm not going to go over it that deeply. You do have to, it is a minor change to change it from, you know, just a regular shortest path to probability. I think we talk about it sometimes is that I think in the past I talk a lot about like you writing something like if P is greater than best of node or something like this, or maybe the other direction. In this case it may be the other direction. But I think a better way to actually write this is actually maybe, or like a more intuitive way to think about it is that we have a used array, and here the idea is just that if it is used rather, oops. And that's all. The idea here is that for every node, the first time we relax it or come to this relaxation process, which is when it comes to when we pop it off the heap, that means that it is going to have the maximum, in this case, maximum probability, or in the shortest path problem, the shortest way is ever going to go, because because in the heap it is sorted. So if it comes later, it's going to have a higher cost, right? So therefore, every edge that goes forward are also going to have higher cost. So you should just skip it. And the reason why this is needed, even though it might not appear in textbooks, is that heaps has a thing called update, or like the theoretical heaps, the heaps that are in the textbooks have a thing that's like an update, just an update function for you to kind of update, call an update, so that it updates a node's value, so that each node will only appear in each heap once. But here, as because of the way that we're doing, it's called lazy heaping, maybe some lazy heap removal, I guess. I forget that. I'm blanking on the term, so my apologies. But it's something lazy. That means that each node may appear in the heap more than once. In fact, it can appear all ye times, where it's the number of edges that it can appear, right? So yeah. So these are the things, and I know that when I wrote it in the past, it's kind of confusing and people don't know why. But now I want to write it in this way in the future, at least for non-contest solutions, so that it's more clear, right? So then if it's used, then we continue because we already done it before. Otherwise, we set it to use, and then and then we just go for all the edges connected to this. P is a terrible name. Maybe a current P. Maybe that's a little bit better. I don't know. But yeah, and then now we have new P is equal to current P times P, right? And then if best of we is greater than NP, or smaller than NP, because we want to maximize it, right? Then we said, is there NP? And then we also put it into the heap. What am I writing? Keeping in mind that in a breadth first, unlike in a breadth first search, is what I want to say, you don't have to check that it is not used. Even though I guess you can, but it doesn't really matter whether you do or not, because I mean, I guess you should just by convention, but you don't have to, because this should take care of it for us. Eventually, as we get more and more edges, this will get big enough that it will never be true, right? So and it doesn't go back and forth because of this, right? We don't relax each, so each edge gets only relaxed once, but maybe checked twice, but relaxed once, right? So yeah, and then at the end we can just return best of n node, and we should be good, because we never updated, it will give us 0.0, right? Let's give it a quick submit. Hopefully I didn't make a silly mistake. Oh no, did I misunderstand this problem? Maybe I did. How did I get it? This is such a wrong answer. Oh, I'm dumb. I was just a little bit late. I was too focused on kind of like just talking about this and the structure that I forgot that heap is a min heap, right, in Python. It doesn't just magically do what it wants, and of course, because it's a min heap, this is going to be keep on giving us the minimum probability, which is not what we want. We want the maximum probability, so we want the reverse version of this, which we can kind of fake by using a negative thing, right? So then here, right, and then maybe we can write current P. We convert it back to the positive version, so that all this makes sense. And then here, when we put it back in the heap, we put negative P. Man, that was just like randomly lucky that it works for the examples now. But yeah, so hopefully that makes sense. We even had a silly mistake just to kind of, illustrate it. Yeah, and I think, oh, I did have this here. Why did this terminate TLE? That is weird. last time? Oh, I made the same mistake last time with the min heap. Oh well. And I guess it probably does something funky. But yeah. What is the complexity here, right? Well, how many items can heap have at most? It's going to be have y number of elements, y being the number of edges, but most of them will terminate before here. So then now, if you want to say, you know, so this has at most y number of elements, because for each edge we push something onto the heap, right? Because we only push something to the heap once for each edge, maybe twice, I guess, from both sides, right? If you want to count that as an edge. So that means that heap will have at most heap number of elements. So this is all of y. But of course, we only relax n times, right? Because of this. So we don't do this for loop y times. We do this for loop n times because this just limits each node to do it once. So that means that it is going to be n log y, or v log y, if you want to call it that. And that's just pretty dexterous stuff, right? So nothing that tricky about it if you're really very familiar with dexterous. And as I would say, dexterous is definitely something that is very much in interview zeitgeist. So definitely work on it, definitely practice it, definitely be familiar with it. And that's all I have for today. Let me know what you think. Thanks for watching. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.